Okay. So you might be looking back at that example of ozone, or like this guy where I said, these are plausible Lewis structures, but they're not the best. What do I mean by that? Like, shouldn't all the sulfur trioxide molecules look like this, or all the ozone molecules look like what we drew? That actually results in this idea of something called resonance, where these Lewis structures, they're an incomplete idea. They can't describe what's actually happening. So let's talk about that. So the next section we're going to have is called resonance. Okay, and we're going to consider the Lewis structure of O3 again. And how did we have ours drawn? We had, did we have a double bond here? Like this, is that how we drew it? Oh, except we had these on top. Like that? Okay, what am I missing on here for it to be a complete Lewis structure? Yep, formal charge on this guy. That one. This guy. Yep. Okay. Now, let's say we were to measure the bond lengths of this. What would you expect this bond length to be, let's say, between oxygen number, said 1 and 2 or 3, right? 1, 2, and 3. Which one would you expect to be a shorter bond length? 1 and 2 or 2 and 3? You would expect 1 and 2 to be shorter, right? And then 2 and 3 would be longer. Why did you say 1 and 2 should be shorter? Right. That double bond means you're going to have more bond energy or a stronger bond strength, but it's going to constrain that distance, right? So one would expect that the bond between oxygen 1 and oxygen 2 would be shorter. And oxygen 2 and oxygen 3, right? Okay, so if you look at the average bonds, what we're going to do, we have a single oxygen-oxygen bond, and we have a double oxygen-oxygen bond. And we're going to keep track of their bond length. It's 148 picometers on average for a single oxygen-oxygen bond. For a double bond, it's 110. Now, if we look at ozone's bonds, we said we would expect 2 different bond lengths, right? When you measure it, like through X-ray crystallography or other methods, what you find is you get 1 bond length. And that bond length is 127.8 picometers. So we're going to ask the question, why only 1 bond length? And something else we're going to look at, what do you notice about the distance, that bond distance? Yeah, it's between these. What's going on here? So the bond length is in between. A single and double bond. What's going on here? Well, we can represent ozone with two different structures. We can represent Lewis structure two ways. So we have our first way. One, two, three. What am I forgetting on this? Yep, formal charge on number 3. Yep, number 2. Yep, 1, 0. You need formal charges to be a correct Lewis structure. Keep that in mind for the exam, okay? Is that the only way we can draw this molecule? Anybody have another suggestion? Okay, so you're saying like this? Like that? Okay. Let's see. 1, 2, 3. What am I missing on here? Yep, charge on 1. Yep, charge on 2. Yep. 3. 0. Which one's correct? Both and none, depending on what way you look at it. These are known as resonant structures. The way that we denote this is we draw the two structures and we show a double-headed arrow. Now, what would actually be a better way to represent this? Like we said, both of these Lewis structures, they're both kind of right, they're both kind of wrong. How would you represent this a bit better? So we actually observe something like do we want a double bond between 1 and 2? Or do we want a double bond between 2 and 3? Do we really even want a double bond? Well, are we as small as a double bond? No. Then do we want a single bond between these guys? Well, we're not really the length of a single bond, right? So what would you suggest to do? Any ideas? Thinking outside the box? Yeah, we would want like a 1.5 bond, right? Unfortunately, with the way that we have Lewis structures, we don't really represent it too often. What we could do is we could do something like dotted lines. Give you an idea of, okay, there should be something else there. And then in this case, all the bond lengths look like they should be the same then, right? They're all experiencing the same amount of bonding. Can you guys see that? Better? Okay. So what's happening here? Well, this is just an inadequacy of Lewis structures. Sometimes we use the term the bonds are alternating. The bonds really aren't alternating. Okay, the bonds are not alternating. It's just that the Lewis structure can't do a good job. Lewis structure does not accurately Nope. How do we spell accurate? Right. Accurate. Be better. Does not accurately describe the bond. Okay, so what we actually observe, this is known as a superposition between two states. It's like a mixture of the two. Depending on when you take a picture of the ozone molecule, it might look like this, or it might look like this, or it might look like this. It's kind of an average of all of those. But so what we can say is these are resonant structures of one another. And if you can draw more resonant structures, you actually have a more stable system. So the more resonant structures, you can draw, it often indicates a higher stability. And next time, we're going to look at a practical reason why this indicates this. We're also going to use it to describe some chemistry. So have you ever really thought about like strong acids? So let's use nitric acid as an example. If we throw this into solution, what happens? Does it stick together like this if it's a strong acid? What's it going to break apart into? Yep, and what else? Okay. But nature hates charges. Why does this happen? We're going to explain that next time. Okay. Are there any questions about resonance or formal charges or anything that we discussed? Yeah?
So are we going to have to move the one on the bottom right with
this? You should be able to draw these and indicate that they're resonant structures.
No, the one
Like this one?
yeah.
No, you don't really know that that's what is actually happening. We'll be able to draw these. Okay? Any other questions?